Good day, everyone, especially to our viewers. So today I will give you a tutorial about the tree of a computer scientist view. So in our nature of tree, the leaves will be in the upper, the branches, and the root, right? But in the point of view of the computer scientist, the root must be the apps, and then next to the nodes and of the branches of this, and last will be the leaves. So now let's proceed to our definitions of tree. A tree is a finite, non-empty set of elements. It is an abstract model of hierarchical structures. It is also consists of nodes with an parent-child relationship. So what are the applications of a tree? So it must be, we can gain organization charts, file systems, and of course we have programming environments we can use by a tree. Next, tree terminology. So here we have an example of a tree. So we will get the property and its value. So we will get the number of nodes. So we will count all of a node. So A1, 2, 3, 4, 5, 6, 7, 8, and 9. So the all number of nodes will be the 9. Next is the height. The height is the 1, the 2, 3, and 4. So it have a 4 height of a tree. The next is we have a root node. A root node is a letter A because um, because it has a node that without a parent, so it must be the A. Next, we have leaves. The leaves here is the D, H, I, F, and C. That would be the leaves. Next is the interior node. So the interior node will be the H, B, A, and G. That. Next, we have the ancestor of H. So first we will find the H. So here, the H here, we will get the, we will go to the G, E, B, and A. So that's that will be the ancestor of H. Next, we have the descendants of B. So we'll find the B. So it would be the D, F, E, G, and H. And lastly, we have I. The siblings, we'll find the siblings of E. So here the E. So the siblings would be the D or the F and D. So next is would be the subtree. So the subtree of and E here, A, the subtree of A. So the subtree of A, but we can say that that is stated here that the subtree of A, but with an exact of right subtree. So the right node would be the C. So that would be the right subtree of A. Next, lastly, would be the degree of this tree. So we will find the degree of this tree. So as we can see, we have 3 degree of its tree. So 1, 2, and 3. So exactly, we have a 3 degree of this tree. So that's example of my tree terminology. So now we will go to the types of tree. What are the types of tree and what it would be? There's a lot of the type of tree, but for now, I will give you only a five more most um, important types of tree. So first, we have a general tree. What is it? So a general tree is a no constraint or a rule is placed on the tree's hierarchy. Every node may have an infinite numbers of children um, in general tree. Next, we have the binary tree. Binary tree is the kind of tree in which most of only two children can be found for each parent. So that would be binary tree. But the kids are known as the left and the right kid. The number Next we have the number 3, we have binary search tree. The binary search tree or BST is a binary tree extension with a several optional restrictions. So it must be the left child would be the less than or equal to the parent value. For example, we have the parent value of 6. So the left child would be a 5 a 6 or down to 0. So because it has a less number. So in the other side, it has the greater than um, and the right and in the right side, it would always be a greater than to an apparent value also. So for example, we have 6 in the parent. So it must be 7 up to, because it would be the greater than value of a 6 or a parent value of a root or a parent. It's called a binary search tree. So now we will go to a AVL tree. What is AVL tree? AVL tree is a binary search tree of Adelson, Welsky, and Landis. So it means AVL. It is an inventors of each specific tree. This was tree that balance and dynamically balancing a factor is allocated for each node in the AVL for tree base and when the tree, whether the tree is a balancing tree or not. AVL3, the correct balance factor is 1, 0, and negative 1. If the node has a new node, it will be rotated to ensure that it is a balance. So that would be a AVL3. Next, the last we have an splay tree. What is a splay tree? A splay tree is a self-balancing tree and at the same time with an AVL tree. So what makes the splay tree unique is the extra property, which is splaying. Why? Because a splay tree contains the same operations as a binary search tree. It has an insertion, deletion, and searching. But it is also contains one more operation. So it would be a splaying. So all the operations of the display tree are followed by a splaying. Now let's proceed to swim deeper about a binary tree. So what is a binary tree? A binary tree is a tree with the following properties. Each internal node has at most two children, degree of 2. Then the children of a node are in of course in or must be in ordered pair. We call the children of an internal node the left and the right child. So, alternative recursive definitions, a binary tree is either a tree consisting of a single node or a tree whose root and ordered pair of children children, each of which is a binary tree. So, of course, binary tree has also an applications. It must be arithmetic expressions, decisions processes, and researching. So, to more deeper, let's proceed to a binary tree example. Binary tree traversal. A binary tree traversal is a specific order in which to trace nodes of a specific tree. There are three common of a tree traversal. First, we have in order. Next, we have pre-order. And lastly, we have post-order. In order, we must follow the rules that left, root, and right. Stated here that in order we must print each subtree's left branch before we print its root. So in pre-order, we have root, left, and right. And lastly, we have post-order. And in post-order, we have left, right, and root. So to more knowledge about this, to more understanding deeper, we must give an example of it. Binary tree traversal examples. We have 15, 5, 3, 12, 10, 13, 6, 7, 16, 20, 18, and 23. So, we will get the in order, pre-order, and post-order of these. So, in order, left, root, and right. So, we have 3. Next is 5, 6, 7, 10, 12, 13, then 15, go to the right side, 16, 18, 20, and 23. And pre-order, we have root, left, and right. So it must be 15, root, 5, left, 3, another left, because it has more left before we go to right. So 12, 10, 6, 7, 13, 16, 20, go to 18, and 23. That's a pre-order. And lastly, we have a post-order. In post-order, we have left, right, and go to the root, before to root. So we have 3, left, 7, 6, 10, 13, 12, 5, 18, 23, right? 20, 16, and lastly, the root is 15. So that an example of binary tree traversal. So another example you want. So we have 8, 3, 1, 6, 4, 7, 8, 14, and 13. So we will get the in order, pre-order, and post-order. In order again, the left, root, and right. So in order here, we must have an 3. We have no. It is a 1, 3, 4, 6, 7, 8, 10, 13, and 14. Next, we have pre-order. Again, also, we have root, left, and right. So, we will find the root. We have 8. Next is left, 3, 1, go to 6, 4, left, and 7. Then we have 10, 14, and 13. Lastly, we have post order. Again, also, it is a left, root, and I know, it is, I'm sorry, rather it is a left, right, and root. So, stated here, we will get the value of left. We have 1, 4, 7, 6, go to 3, then 13, we have 14, 10, and lastly the root, we have 8. So, this example, we can call this as an binary tree traversal. So, that would be all. Thank you so much. I hope you enjoyed this video and more gain knowledge about my discussions about a binary and the types of binary. So, thank you so much. Bye. Enjoy.